Am I audible? Am I audible in the back? Am I audible in the back? अभी भी? Am I audible now? No? Is it audible now? Am I audible? This means no, this means yes. वहां पे वो कह रहा है उसको सुनाई दे रहा है, तुम्हें यहाँ नहीं सुनाई दे रहा, तो तुम पीछे का मत बताओ, तो अपना बताओ. Am I audible in the back? Deepak? Volume is less. Is it better now? Am I audible? Okay. So we take care of ourselves when it is asked audible. Okay. So before we go deeper into it, a few class logistics. I know you've been waiting for formal announcement of office hours, while sporadic office hours have been announced in the Google Classroom and you've been attending those. How many of you have been utilizing the office hours already? Oh, so we are announcing, but no one is coming. Are office hours needed? Then when we are announcing, why didn't you go then? So we'll see. So as I said that I will keep 2 office hours. There is one set of office hours I have planned for over the weekend. But if there is no one in the weekdays also, there's no point in coming online on the weekend either. So if the office hours are underutilized, we will retract them. Is that okay with all of you? Is that fair? So there is some form of engagement almost every day of the week with MDT. So let us make best use of it. It's a Please close this. So बाहर रौनक किस चीज की है? You know that? What is happening outside? It's quite a bit of a rush there. So, okay. Have you noted this? The weekend office hours will be announced by Friday. कि उस weekend पे कौन-कौन से time पे whoever is available, they will announce by Friday. Other office hours are fixed. Any constraints? Anyone has any constraints around these timings? 2 to 3:30, 2 to 2:30 to 3:30, I think everyone would be able to intercept at least half an hour. And for my office hours on 10th at 10:30 on Wednesday, 10:30 to 11:30, even if, how many of you are doing AELD? So even then, after the AELD class, you can intercept my hours. Am I right? Sorry? Evening. So you want me to work over evening and Saturdays and Sundays? I'm already doing that, but at least not in a formal office hour engagement. So you want evening office hours. How many of you prefer evening office hours? What time? 11 p.m. over here in the office? Arpit kah raha hai, haan, please. So how many of you prefer evening office hours? No, it's not a joke. I really want to understand. When you say evening, it means after 6 p.m. Then afternoon office hours. So I know I have classes in the second half also. I'm taking 2 courses. That second course is in afternoon. So you say that most of us, but you again are representing yourself. Am I right? How many of you have a strong preference for afternoon office hours over morning office hours? Will something like so the challenge is 2:30 to 3:30. There is also already one office hours announced for Wednesday. You already have one set of afternoon office hours. So when it comes to me, that blocks my time in a very peculiar way that I have to do something after 3:30, and that I also need some formal slot for my other engagements and meetings. 2 days I'm already blocked with classes. Uh, okay, let me see what time slot I can arrange on either of Monday, Wednesday, or Friday for the evening office hours. Then I will remove the Wednesday morning office hours. I will see and I will come back to you. Okay. Any other constraint, concern that you have? How many of you have classes in the afternoon? On Mondays, Wednesdays, or Fridays? How many of you have classes? What timings? Mondays, Wednesdays, or Fridays? How many of you have classes in the afternoon? What time is that? So you have a class from 3 to 4:30 on Mondays, Wednesdays, and Fridays. Fridays also. Mondays and Wednesdays, you have a class from 3 to 4:30. Okay. So, so then the only time that remains for me is either 2:30 to 3:30 or 4 to 5. So that every one of you has some access. I will, sorry? See, Arpit, what that does is that clearly gives me a majority. And then again, a few of you will feel cheated that, yaar, mere ko to sir se mulaqat nahi ho pai. Mhm. So that is why I'm asking at least those people who are here in the class. Those who are not in the class, they lose. But at least those who are here in the class, you have the first right to influence the decision. So I will see if I can manage the 2:30 to 3:30 slot, but that is already with Mayank there. So that is not an option. So the only slot is 4 to 5 slot then. I will see if I can manage the 4 to 5 slot and I will let you know. So it is either 10:30 to 11:30 on Wednesdays or 4 to 5 on Wednesdays. I will update you and the Google Classroom. For the other TAs, the office hours are fine. Okay. So a quick review of the kind of optimizations we looked at for memories. We said that based on the kind of design, someone may want to have an optimization towards high density or high speed or low power. And this can result in the change of the memory cell. That's the first thing that will change because that has the biggest influence on both timings and area and power, everything. And when you want speed, you would typically want to have a larger memory cell. That larger memory cell will have better current. Better current means better speeds, but the area goes for a toss. And a low power memory cell might have a larger footprint because you might have more transistors to enable low power, or might be higher VT in the small footprint itself. So that leakage is further reduced, but that would have a significant impact on speed. So as a memory designer, you will have to make not only choices around memory cells, but you will also have to make choices around what kind of sense amplifiers, which kind of sense amplifiers. We also looked at the hierarchical bitline architecture, where we said that a hierarchical architecture would lead to shorter bit lines, lesser power, better speed, but clearly more area. So all those optimizations we have to consider when we design a memory compiler. And after that, we had moved to the zone of designing the SRAM cell. So for the 60 SRAM cell, we saw that so for the 60 SRAM cell, we saw that uh, clogged data latch, how that moves from a 16 or 14 transistor configuration into a 6 transistor configuration. And we understood that there are going to be some constraints that this transition from a 14 transistor fully CMOS design into a non-CMOS uh, skeletal design will bring. But we said because in memories area is diamond, we are ready to face that challenge. As designers, we will face that challenge, we'll fight it out, and we'll overcome it. That was what we agreed upon. Are you with me on this? Any questions until here? So until here it is clear. Then we looked at the read and write operation in the 60 memory cell. How do you read inside a memory cell? Okay. So we have the bit lines. We have the bit lines preconditioned, pre-charged, and when the word line comes, one of the two pre-charged bit lines will discharge. The side on which 0 is stored, that particular pre-charged bit line will discharge. And as that discharges, we will be able to measure the differential in the sense amplifier in the IO region and give an output 0 or 1 depending on whatever logic we had stored. Are you with me on this? The read operation is clear? Any questions about that? So a quick review of the write operation then. How do you do the write operation in a memory cell? So we again precondition the bit line. In the read operation, the preconditioning was both bit lines are pre-charged. In the write operation, the preconditioning may mean that one of the two bit lines is discharged. Hmm? So we again precondition the bit lines. And when the word line comes, the memory cell, depending on however the bit lines were preconditioned, will first write a 0 inside the memory cell. And then after the 0 is written, the 1 operation is completed. So why is a 0 written before the 1 operation? Why is it like that? Okay. We had discussed in the last class also this, that since NMOS cannot transmit VDD very strongly, it can only take an internal node to VDD minus VT. The internal PMOS, the PMOS inside the memory cell has a role to play. The PMOS inside the memory cell has to turn on so that we can write a 1. To turn that PMOS on, the other side should have a 0 written into it. So essentially, 0 is written before one write can be completed. This is for the case of NMOS pass gates. If I were to design PMOS pass gates, forget about one has to be written first. What is the preconditioning that you would probably want to do on the bit lines during a read cycle? Both to 0. Okay. And during the write cycle? Both to 0. So again, for the write operation, the preconditioning will remain the same. For the read operation, the preconditioning will change. And what we are also expecting then is that uh, in the write operation, 1 will be written before a 0 is written. Are you with me? So combining these various operations and constraints that we built into the memory cell, we need to now look at how do you evaluate memory cells. See, if I tell you that in memories area is diamond, and I say that you need to go and purchase some diamond jewelry from a jeweler. There are some criteria on which you will evaluate a diamond. What are those criteria? For a regular diamond, those criteria would be what is the clarity of the diamond, what is the kind of cut of the diamond, what is the color of the diamond, uh, brilliance, and so many things. Obviously, the weight, the caratage. So, caratage is the first thing, but then all other things also come in. So, for us also, when we talk about memory cells or when you talk about any design, you need to compare and benchmark and validate that your choice is in line with what you wanted to do. Am I right? So there are a few figures of merit that have to be ensured or that have to be uh, evaluated before finalizing your choice of memory cell over there. And in the slides also, you saw these few figures of merit. But which figure of merit is not even mentioned here? Area. Why have we not mentioned it here? It is the most important. Now, if you want to go and purchase diamonds in the market, caratage, that is the weight of the diamond, is anyways the most important thing, is it not? So you do not just evaluate diamond on color, cut, and other stuff. Caratage is the base. Okay, 1 carat ka diamond le rahe ho. Now we look at what is the other things that, how are the other things moving? So area is so important a figure of merit for SRAM cells that the SRAM cells are named or referred to by designers by the area. Oh, let us look at a 512 HS cell. So 512 stands for the area, HS means high speed. Or 512 LP, which means low power, where the cell area remains same, but you might have used different VT implants or probably different gate lengths to reduce leakage or dynamic power or whatever. Are you with me on this? So area is clearly the most important figure of merit, but we have not even mentioned it here. But we have mentioned these 7 figures of merit, which are distributed across power and performance. Are you with me on this? So with every to reflect and then tell me whether that figure of merit is linked to power or performance or both. Is that okay? So the first figure of merit that we have over here is the cell current. What do we mean by the term cell current? It is the current that the memory cell thinks when the word line is turned on. So what will it directly influence? What is the direct outcome of a larger cell current or a smaller cell current? If the cell current is larger, the discharge rate will be higher. What is discharge rate? The rate at which bitline capacitance is discharged. That is discharge rate. Given the same bitline hierarchical architecture or bitline architecture, a larger cell current would result in faster discharge. So discharge rate is higher. If the discharge rate is higher, what happens to speed? The delay reduces because now you are able to hopefully provide differential at the sense amplifier inputs faster. Are you with me on this? So सेल करंट के साथ मैंने एक अभी नया टर्म जोड़ दिया आपके लिए, डिस्चार्ज रेट. If I have to estimate the discharge rate of a bit line, what matlab, this is very basic. You don't need a memory course on this. This is a very fundamental foundational question I'm asking you. If I have to estimate the discharge rate of a memory cell or a bit line, what all information do I need? The size of pass gate and DMOS, no? Resistance in the path and VT of transistors. Okay. So do you realize what I also need is the capacitance of the bit line? All those things will help me determine what is my cell current. Is it not? जो भी आपने बोला VT of the pass gate, this, that. All that is what we talked about in the lecture. I told you that I'm going beyond the lecture. So if I have to find the discharge rate, I need to know the capacitance of the bit line. Is it not? So do you realize that there now could be multiple ways to improve speed? One is through increasing the cell current. But if I have to improve speed, I can also reduce the bit line capacitance. That is what we were trying to do when we were folding using mux there. Is it not? So speed is not just a factor of bit cell current. However, cell current is clearly a performance figure of merit. Are you with me on this? Any questions until here? So what does the cell current depend on? Cell current depends on the two transistors which are in the current path. Bit line was pre-charged to a particular level, let us say VDD. And then when we turn the word line on, this particular path opens up. So what we are essentially looking at is that if I increase the sizes of PG and PD, or if I reduce their threshold voltages or something like that, I will be able to have a better cell current over there. Now bitline leakage. This is bitline leakage we're talking about, not total leakage yet. What is bitline leakage? In a memory array, we would have every bit line connecting more than one cell. At least few cells will be there on every bit line. And when you're doing a read operation or a write operation, only one row will be on. Remaining all the cells are off. The word line is 0. But every bit line, when it is connected to so many number of cells, there will be some leakage that will exist. So the leakage of the memory cell for the bit line is an important figure of merit. Why is it important? Is this a power figure of merit or a performance figure of merit? Primarily, is it a power figure of merit or is it a performance figure of merit? Primarily. How many of you say power? Okay, how many of you say performance? So actually, bitline leakage, as we are evaluating it over here, is primarily a performance figure of merit. Why? Because the leakage on the non-discharging bit line will have a significant impact on the rate of differential creation. जो हमने अभी पहली बात करी, that was about discharge rate. That was about the bit line which was anyways expected to discharge. Let's look at it like this. My bit line was pre-charged to VDD. As the word line turns on, or as the word line turns on, this bit line will discharge at this rate. Okay. Now let us say I had a very leaky bit cell in terms of bit line leakage is very, very high. So we also saw that Before in the signal flow diagram, we also understood that for the bit line to discharge as soon as the word line turns on, precharge would have to be turned off before the word line arrives. See, if the preconditioning transistors are on, so precharge is on, even when the word line is there, those transistors are going to be huge because they have to charge the complete capacitor. They will easily overrun the sink of current from the memory cell. That's going to be a small current. So before the word line turns on, your precharge should be off. This is a very important race condition that exists inside the memory. So let us say my precharge turned off somewhere here. Okay. And my bitline bar, which was precharged to the same level, now it will start to leak. Are you able to see that bitline leakage I have shown to be lesser than bitline than the cell current? Uh, So I'm not being unfair in saying that the bitline will leak as soon as the precharge turns off. And when the word line comes, after that, this will continue to discharge like this because this is leakage. And my memory cell will continue to have a discharge like this. Now, you know that you can turn the sense amplifier on only after a sufficient correct differential has appeared at the bit lines. It's like an op amp. You have to overcome the offset of the op amp there. Suppose that offset is 100 millivolts. Let us say 0.1 volts, 100 millivolts. So we want this difference to be 100 millivolts before the sense amplifier is turned on. So your precharge went off here, your word line came up here, and finally you can trigger the sense amplifier on somewhere here. Are you with me? Now let us say we were very conscious of bitline leakage. And we had made a cell which has lower bitline leakage. Then how would the situation look? Bitline will still start to leak at the same time, but now at a different slope. Are you able to see this? So in this case, I could have possibly turned on my sense amplifier here. Are you with me on this? So when I reduce bitline leakage, yes, I reduce leakage. It's a power figure of merit also. But very importantly, I improve speed. Are you able to see this? So bitline leakage per se, is primarily a performance figure of merit. It is definitely a power figure of merit also because it is talking about leakage. It is some current that you do not want to flow, but it is flowing. But it is primarily a performance figure of merit when I'm talking about it over here. Are you with me on this? So what we are saying is that I will change the order now. We know that for the sense amplifier, I need 100 millivolts of differential between the bit line and the bit line bar. यहाँ तक clear है सबको? This is an assumption I'm making. Now, what I need is that I turn the precharge off, I bring the word line on. I want to trigger my sense amplifier as early as possible. Suppose the leakage of the bit line leakage was corresponding to this particular line, the top one. Okay. So the bit line leakage will start to discharge the non-discharging bit line before the word line comes also. As soon as the precharge goes off, it will start to discharge the bit line. So we see that as soon as the precharge goes off, the non-selected bit line will start to discharge. Now your word line comes. The discharging bit line now starts to discharge the read bit line. So this is how it follows. Now you know that if this is my other bit line and this is my discharging bit line, yahan pe jaake 100 millivolts has been generated. I can trigger the sense amplifier enable here. If the leakage was higher, the situation would be what we have on the lower side, where because leakage is happening, to create that 100 millivolts differential between the bit line pair, I need much longer time for discharge. Are you able to see this? Now, if my sense amplifier comes late, performance clearly goes for a toss. What other thing happens? So अभी तक आपने बिटलाइन लीकेज को पावर फिगर ऑफ मेरिट खाली इसलिए कहा बिकॉज आपने वहां पे लीकेज, यू जस्ट रेड द वर्ड लीकेज. I want to bring your attention to another aspect, which is far much more power than the leakage itself. Realize that if my bitline leakage is more, then my bitline, my real bitline or discharging bitline has to discharge until this level. And this leakage, and otherwise it would have discharged only to this level. कहने का मतलब, when the bitline leakage is low, I could have possibly triggered the sense amplifier by discharging the real bitline or discharging bitline down to, let us say, 120 millivolts, saying that 20 millivolts was the discharge on the leaking bitline. But if the bitline leakage is larger, then I might need to discharge the bitline down to 150 millivolts because the leakage was more. Because what happens is, see, as I move from here to here, my leaking bitline has also discharged a few further millivolts. So I have to discharge much more than the bitline leakage that had increased. Are you able to see this? So it is not just because of leakage that this is a power figure of merit, but also because of the fact that my bitlines, which were to be read, will now need to be discharged more. That is wastage of power. आपने सेंस एम्पलीफायर क्यों लगाया? So that थोड़े से डिस्चार्ज के बाद आप वापस प्रीचार्ज कर दो. But now थोड़ा सा डिस्चार्ज नहीं बचा. Now I have to discharge further more. And therefore it has a power marginality or a power figure of merit also. Not just because the term has leakage in it. Are you able to see this? So discharging bitline will also have leakage, right? So in the worst case, we are saying discharging bitline is having negligible leakage. In fact, we are saying that if there were 1,000 cells connected to a particular bitline, only one is having zero on this side. All the other 999 have zero on the other side. So there is no leakage. The NMOS ke through, you do not expect VDD leakage. So VDD is written on this side. दूसरी तरफ VDD minus 100 millivolts hai, minus 150 millivolts hai. Even the VT of the NMOS is not there. So you do not expect VDD leakage to happen across the NMOS. But we are saying that for the worst case leakage, bitline leakage calculations, we will assume all the other cells in the particular column have zero stored there. Are you with me on this? So I could have turned the sense amplifier on over here. What is the level of bitline here? Let us say some X discharge has happened. But if I turn the sense amplifier on over here, clearly this is X plus delta X discharge that has happened. Is it not? That is all that I'm saying. That is more power, na? If you discharge the bit lines more, you have to spend more power to recharge it now before the next cycle starts. The difference between BL and BLB has to be 100 only. That we have remained fixed. That we have kept fixed. But do you realize to get that difference, my bit line has to discharge much more now? Are you able to see this? So the difference I have kept fixed because I am not changing the sense amplifier. The sense amplifier requirement I have to assume to be the same. Otherwise, I will be comparing apples with oranges. So for the same bitline differential, I now need to discharge bit lines for a longer duration. They have to go to a lower voltage, so they will need to be pre-charged. So power also. That is why power. Not just because leakage likha hai to power. Are you with me? But primarily performance. Yes. कहाँ हो रहा है बताओ? If this is my leakage, if this is my leaking bit line, if this is my leaking bit line, when do I get 100 millivolts? Only here, na? इससे पहले तो 100 से कम ही है ना? That is a lower leakage scenario. In the lower leakage scenario, that is where we could turn on the sense amplifier earlier. That is exactly what I'm saying. If the bitline leakage is lower, you can turn on the sense amplifier faster. So you gain speed. And also bitlines will be required to discharge less. So you have lower power. If bitline leakage is more, you have to delay the sense amplifier on condition. So the bitlines will discharge for much longer duration and will also consume much more power. And overall operation will also be slow. Exactly the same thing that you are pointing at. But are you able to see this? आप दिखा वही रहे हो मुझे, मैं आपको वही बता रहा हूं. Are you able to see this? आप बताओ. जो लीक हो रहा है उसका लीकेज इग्नोर करेंगे तो फिर बचा क्या? तो हम बात ही क्या कर रहे हैं? हमारा फिगर ऑफ मेरिट ही बिटलाइन लीकेज है ना. तो हम लीकिंग बिटलाइन को कैसे इग्नोर कर सकते हैं? हम कह रहे हैं जो डिस्चार्जिंग बिटलाइन है उस पे लीकेज का इंपैक्ट नहीं आएगा क्योंकि उस पे उसके कॉलम में हर तरफ 1 ही लिखा हुआ है. एंड NMOS will not leak a 1. That is what we are saying. Is it clear? Any questions? So bitline leakage is dependent primarily on the size of the pass gate and the VT of the pass gate. अगर पास गेट का VT लो रहेगा तो लीकेज ज्यादा होगी, साइज छोटे से छोटा हो तब भी. Are you with me on this? Okay. So then coming to cell stability. What do you understand by cell stability? How many of you have watched the lectures in advance? Okay. So what do you understand by cell stability? Why is cell stability important? Okay. See, look at it like this. When I say that I'm storing some information inside the memory cell, suppose आपने एक बैंक में 100 रुपए जमा कराए. You deposited 100 rupees in your bank account. That's a storage vault. छोड़ दो bank account. Let us say there is a locker that you have in a bank account. How many of you have? So all of you have a bank account? Anyone of you has a locker? A few of you have. Your parents have a locker? So suppose your mother deposited some jewelry in the locker. So the locker was filled. Someone went to inspect, someone simply went to inspect if there is something in the lockers or not. Just something in the lockers or not. So, they have developed a new machine just to see how many people are using their lockers. This machine can do an X-ray. It still cannot find out what is inside the locker. But is there something in the locker or not? They have gone to inspect, empty or filled. That is the only thing I want to know. And after they do this checking, when your mother goes to retrieve her jewelry, the jewelry is vanished. Is this a good locker? Nahi na? Would you put your jewelry in such a locker? Such a bank? No. So when we talk about storage, the most important thing is that the contents of my locker should remain intact. Is it not? So now, if whether I'm doing any scanning outside or I'm sweeping the floor outside the locker, I'm doing whatever around the locker, I have not even opened the locker. Or I have just one key to the locker. See, bankers have one key to the locker, you have the second key. If only with one key, I'm able to retrieve the contents and take them away, that's not a good thing. So during the read operation, there is only one key that is available, the word line. For completing a write operation, you need the second key also, the bit line. Now, suppose during the read operation itself, only the banker key is available and the contents evaporate, contents change. That's not a good cell. That's not a good storage element. So, memory contents have to remain stable during read operation. This is the foremost requirement of any storage element. Are you with me on this? Just because someone went to sweep the floor outside or someone stole the banker's key from there, nothing should happen. Similarly, someone stole your key and rushed to the locker to extract. Again, nothing should happen. तो चाहे bitline discharge हो गई और word line नहीं selected, nothing should change. Or word line select हो गई, bitline has not been preconditioned for a write operation, nothing should change. Are you with me on this? So that is what we mean by cell stability. And after area, this is by far the most important figure of merit. Now, is this a performance figure of merit or a power figure of merit? Performance? How many of you say performance? How many of you say power? All of you are wrong. It is neither. It is a functional figure of merit. If this figure of merit fails, the primary function of your cell has been violated. You're not bothered about performance, you're not bothered about area, you're not bothered about anything now. The contents have been lost. Now, are you bothered whether this locker was bigger or smaller? Whether you are paying 1,000 rupees rent for it per year or 1,000 or 5,000 rupees? No, it doesn't matter. This locker is useless. It is not about the size of the memory cell also. The functionality is gotten violated. Are you able to see this? So, while you have to take care of area, if you do not take care of this functionality, that area is also useless. Do you realize? It is a functional figure of merit. It simply cannot fail. Is this clear? Hmm? So when it comes to cell stability, which all transistors have a role to play? You had a question. Is that okay with you? So, nothing. It is still a bad cell. You tell me, if the diamond jewelry was lost, but the copper one was still there, is it okay with you? किसके लिए ओके अभी इस क्लास में? अपने लॉकर्स की तरह चाबियां मेरे को दे देना, मैं खाली डायमंड ज्वेलरी चुराऊंगा और कॉपर वाली छोड़ दूंगा. नो वन ना. The contents of the memory cell should not be disturbed at all. Ever. If I have only one key, the contents have to remain intact, irrespective of what the contents are. Are you with me? That we'll look at later. But if the content is not there, that's a bad locker. So in DRAMs, leakage is natural. It's a part of the process. So in DRAMs, we say that before the contents are lost, we will refresh it. है ना? So there is extra power that goes in the refresh process. There are some cycles which are wasted in the refresh process. But yes, if we know that this is the nature of my memory cell, then I think I can think of methods to replenish and refresh. But you tell me that this is a static memory cell and then the contents vanish. It's not a good cell then. Are you with me on this? So what happens when just one key is available? Only the word line is there. The bit line is not there. So it is a read cycle. So what happens then? Then this is the kind of a circuit that comes into picture. This is the only active part of the memory cell then. The PMOSes are off. The other side is also not doing anything. It is just leaking. So this is the only part of the memory that is active at that time. So what will happen in such a scenario? Bit line is at VDD. It is discharging. To be able to discharge, there has to be a potential difference between two nodes. Is there a potential difference? Yes, bit line at VDD and ground. Now there are two transistors in series which come in between. For current to flow from first transistor to the second, there has to be some differential there also. So this node in the middle, over here has to go lower than VDD. It was written, VDD was, there was 0 written over here. Now, if this node remains at 0 and continues to remain at 0 somehow, do you realize it's not a physical possibility? Because then no current can flow from the second transistor over here, the pull down. So to have any current flow from the pull down, and basically the Kirchhoff's law will be violated. You are trying to sink current from the bit line, but it's not going anywhere. At any Kirchhoff's current law states that at any node, the incoming current and outgoing currents are to be the same. Isn't that just the case? This is the Kirchhoff's law. The first law of electronics that you must have studied in your first course on electronics is that current entering the node has to be equal to the current exiting from the node. So at this particular node, if there is some current entering, that has to exit also. For any current to exit or to be transmitted from a device, there has to be some VDS. It means this particular node will rise a little. Are you with me? So for the read operation, this node is bound to rise. As this node rises, this was meant to be 0, but it has risen above 0. What happens? The NMOS on the other side can now turn on. And it's a latch, so it can latch the other data. So I can lose my contents. So the way to handle stability is, or the way to benchmark stability is to ensure that the voltage Vx generated at the middle of this potential divider is less than the trip point of the inverters there. The latch is made of two back-to-back inverters. So before their trip point is reached, this one should not exceed that trip point, the Vx there. Are you with me on this? So what do you need? You need that the pull down has to be much larger than the pass gate. Pull down has to be lesser resistive, much lesser resistive than the resistance of the pass gate. Is this constraint clear? See, these constraints on designing and sizing are coming because we are no longer a CMOS design. And when we were sizing, we said that, or when we were transitioning from those 14 transistor cells to these 6 transistor cells, we said, okay, all these sizing constraints, ratio constraints, we will look at and take care when we are designing the cell as a designer. So we committed that. Now we have to take care. So these are new figures of merit that we have to ensure are stable, positive, and handled well. Are you with me on this? Any questions? So then that node is also driven by VDD from the PMOS up there. So but that PMOS has a 0 on its gate, has a 1 on its gate. The PMOS is off. You know? If the other side starts to write, that is the flipping starts, then yes, the PMOS will also turn on. That is what I'm saying. The latching action will start to happen. So we do not want that to even get triggered. That is why this ratio, PG to PD ratio, has to be such that pass gate is far more resistive than the pull down. Are you with me? The other side pull up is on. It had a 0 at its gate. Now you raised it a little. You're saying that it is dependent on PG and PD. If we reach PD, just focus on P, then also it will be fine, right? Because Vx will rise and it can turn on the NMOS of the other side, right? So it can discharge the PLFI side and corrupt its data. So we are saying that we are sizing the pull down so that it meets the current. But if we keep the pull down as its like whatever size it was earlier, and size the pull up on the other side stronger, so that it can over the PLFI side better. So then we don't need to size the pull down. See, we already saw when we looked at cell current that you want to size pull down and pass gate large to have better cell current. So you can't say I can keep my pull down to be the minimum sized one. By the approach you are saying, you're now saying that pull up can also not be the smallest size. And you've not yet looked at the consequence on the right operation. You're ignoring the right operation as of now. You're not, because you've not touched that yet. Let's go there. We will see. थोड़ा सा इसको अपने जो मन की क्यूरियोसिटी है उसको रखो अपने साथ. Then let's look at this. Now, if I say that I will keep a very, very large pull down and maintain a very small pull up, what will happen? The trip point of my inverters will go low. So even though I was following the diktat or I was following the recommendation that my pass gate should be smaller than the pull down and my pull down should be much larger than the pass gate, if I increase the size of pull down much larger, then again there is a challenge that the trip point of the inverter will go low and my cell will again become unstable. So there has to be some sweet spot where I cannot size the pull down smaller than this and I cannot size it larger than that either. Are you with me? The input voltage at which it will start to transition from 0 to 1 or vice versa. So the trip point, if the trip point is low,